This video is on chapter 27 on series, and we are going to look at several examples and one theorem in this chapter. So again, you have the notes in front of you. At this point, I am assuming you have studied the definition of what a series is and the notation. So we get to example 184. We have the series, the sum n equals 0 to infinity of 1 over 2 to the n. Recall from example 151 that this series converges. The series of I equals 0 to n of 1 over 2 to the I, n goes from 0 to infinity. Recall that this sequence converges to 2. Now, what is the sequence? This sequence is a sequence of partial sums for this series. Therefore, the series n equals 0 to infinity of 1 over 2 to the n also converges to 2. Because a series is a sequence of partial sums, and we have already seen that this sequence of partial sums converges. Definition 185. The harmonic series. The harmonic series is the series n equal 1 to infinity of 1 over n. So the first partial sum is 1. The second partial sum is 1 plus 1/2. The third partial sum is 1 plus 1/2 plus 1/3, etc. The sequence of partial sums is increasing. Keep that in mind as we look at theorem 186. So this is the harmonic series. Theorem 186 the harmonic series diverges. And we will prove this using induction. So our proof. For each n and n, so for each natural number n, let's set s sub n to be 1 plus 1/2 plus 1/3 up to 1 over n. In other words, Sn is the nth partial sum for this series. Our claim for each n and n, s sub 2 to the n is greater than or equal to 1 plus n over 2. This is our claim. So we're not proving something about every single partial sum. We're just proving something about the partial sum where index is 2 to some natural number. And our proof of claim this is the proof that is by induction. So since S sub 2 is 1 plus 1/2, which for n equal to 1, our S sub 2 is 1 plus 1 over 2. The claim is true for n equal to 1. So let's go to the inductive step. Suppose the claim is true for k in n. So for the inductive step, we want to prove that the claim is true for k plus 1. Then we want to consider S sub 2 to the k plus 1, and we want to show that that is greater than or equal to 1 plus k plus 1 over 2. So let's consider this term. This is equal to S sub 2 to the k plus some stuff, right? So we start with this, and now we have 2 to the k more terms to consider. So we have 1 over 2 to the k plus 1. That is the next term after S sub 2 to the k, plus 1 over 2 to the k plus 1, out to, where do we stop? 1 over 2 to the k plus 1 with the k plus 1 in the exponent. That's where we stop. Now, by the inductive hypothesis, this term is greater than or equal to 1 plus 1, or 1 plus k over 2. So that is greater than or equal to 1 plus k over 2 plus the rest of these terms. Now, these terms here all go out to 1 over 2 to the k plus 1. So these denominators here are all less than 2 to the k plus 1. So I have this from the inductive hypothesis. Now for the rest of these terms, I'm just going to look at the fractions. This is 1 over 2 to the k plus 1 plus 1 over 2 to the k plus 1 out to 1 over 2 to the k plus 1. Now we'll do some algebra. This is equal to 1 plus k over 2 plus 1 over 2 to the k plus 1 multiplied by the number of terms that we have from here to here. Well, how many of those terms do we have? We have 2 to the k. Keep in mind that 2 to the k plus 1 is 2 times 2 to the k. So that's why we have 2 to the k of these terms. So we have 1 plus k over 2 plus 1/2. This is 1 plus k plus 1 over 2, which is what we want. So, the claim is true for k plus 1. Therefore, the claim is proved by the principle of mathematical induction. I'm not going to spend recording time writing that, but this is the end of the proof of our claim. The claim is now proved by the principle of mathematical induction. The theorem is not yet proved, but the hard part of it is. So now, by the claim, the limit as n goes to infinity of s sub 2 to the n greater than or equal to the limit as n goes to infinity of 1 plus n over 2, which itself diverges. So each one of these terms is greater than or equal to each of these terms. Since this sequence diverges to infinity, this sequence diverges to infinity. Remember, when I presented the definition of the harmonic series is an increasing series. So we looked at the sequence of partial sums. That was an increasing sequence. We've only looked at a subsequence, but the ones between 2 to the n and 2 to the n plus 1, those are all between s sub 2 to the n and s sub 2 to the n plus 1. So this is an increasing sequence. And we've shown that a subsequence diverges to infinity, so this implies that diverges to infinity. The last thing I want to do from this chapter is example 187. Example 187 has 3 parts, but they are related. So I'm going to use the parts A and B to talk about part C. So example 187, determine whether each of the following series converges or diverges. Part A is the sum, we start at 2, n equal 2 to infinity, of 1 over n squared minus n. And if you recall from our technique of integration, where we had a partial fraction decomposition, that's what we're going to do with this fraction. We're going to do a partial fraction decomposition on this fraction. So we can rewrite that as 1 over n minus 1 minus 1 over n. So we used a partial fraction decomposition to get that. Now, if you let s sub n be the nth partial sum, what is that? So n starts at 2. So we have 1 minus 1/2. What about when n is 3? Then we have plus 1/2 minus 1/3. And what about when n is 4? Plus 1/4 minus 1/4. That goes all the way out to negative 1 over n. Remember in Calculus 1 when you were learning to integrate and you were looking at these summations and you had something called a telescoping sum? That's what's happening here. This S sub n, this is a telescoping sum. It collapses to 1 minus 1 over n. So if we look at this limit as n goes to infinity of S sub n, that is the same as the limit as n goes to infinity of 1 minus 1 over n, which is 1. So the series n equal 2 to infinity of 1 divided by n squared minus n is equal to 1. So this series converges to 1. For part B, we have the sum n equal 1 to infinity of 1 over n squared plus n. Again, if we decompose this, so our partial fraction decomposition, we take this denominator factors to n times n plus 1, and so we write this is going to be 1 over n minus 1 over n plus 1. This is how this decomposes. Now I'm not going to go through the steps to show you how this telescopes. You can do that on your own. But what happens here is each S sub n is equal to 1 minus 1 over n plus 1. So again, write this out as write out each Sn as a sum like this, and you'll see that it's a telescoping sum. Well, the limit as n goes to infinity of S sub n then is the limit as n goes to infinity of 1 minus 1 over n plus 1, which is 1. What this tells us then is the series n equal 1 to infinity of 1 divided by n squared plus n is equal to 1. We'll use parts A and B to do part C. Part C is a sum n equal 1 to infinity of 1 divided by n squared. Now we use parts A and B to do this. So we saw from part A that the sum n equal 2 to infinity of 1 divided by n squared minus n is 1. And we saw from part B that the sum n equal 2 to infinity of 1 over n squared plus n is 1/2. Now we didn't quite see this in part B. What we saw in part